Yes. So thanks for being here. Last talk of the ITAMP Fest. I'll be talking about optics. And seeing that this is the ITAMP Fest, I looked at our logo again, and like ITAMP, you might have thought about it, like Institute for Theoretical AMO Physics, Atomic, Molecular, and Optical Physics. But somehow, like doing optics, you can feel a little left out or left behind.
Try to pronounce it.
ITAMP. Anyways, I mean, Mercedes just gave a very nice talk about optics, so we will go like a bit more like into the photonic direction and keep talking about optics. So I promised something about quantum light, and basically what I mean by that is any light that is not described by Maxwell's equations. So, for example, light that shows anti-bunching, photons that are entangled, show negative quasi-particle distributions, and so on. And so there's an entire, like there are different fields of what you can do once you have like this quantum light. So it's, for example, an active area of research, what happens if you have entangled pairs of photons, how they interact with matter, how are they absorbed. That's in chemistry, that could be, for example, interesting for spectroscopy. You can also use squeezed light for metrology, of course, that's kind of famous. And quantum light is used in quantum communication, of course, and even in quantum computation, if you use, for example, cluster states of light. But to reach all of these things, like what you basically need to do is you need to be able to create this quantum light, you need to be able to manipulate it, to interface with matter, and you need to also be able to measure it. So that's kind of, these are the requirements. And maybe like kind of that's a science fiction world where like lightsabers actually do interact, and like we do get like these nice battle scenes. But in reality, photons do not interact, or they do not like to interact at least. And so the point of this talk is kind of to show you ways in which you can make them interact. So an important resource for all of this are single photons. Single photon sources, and actually the two leading platforms for this are quantum dots, so basically impurities in a semiconductor that then emit single photons. But like there's some limited efficiency, like as to how efficiently you can outcouple the photons. So it's like kind of emitted into all sorts of directions. So how well do I get it in some sort of fiber? Also, if you have multiple quantum dots, there's limited indistinguishability of the photons that are produced. And I guess the leading rival technology that is commercially used is SPD, so spontaneous parametric down conversion. The idea here is that you like pump a crystal strongly, and so the pump photons get split into a signal and an ether photon. And then you can, for example, post-select on the ether and just use the single photons from the signal. So here, there's like kind of, it's probabilistic, like on whether or not you create like one of those signal ether pairs or not, and that probability is actually fairly low. Okay, but I mean, like these are the dominant commercially active or like used approaches. And when you have single photons, you can build more complicated quantum states, for example, cluster states of light. And so what I will do is like to show you an alternative way of producing entangled states of photons that use Rydberg interaction. And so basically I divided this talk into three chapters, so three different approaches basically, and I would just want to give you an overview or a feeling like on these three different strategies that all are connected via these Rydberg interactions. And these different projects, of course, involve a number of people. So the group of Thomas Pohl from Aarhus, Susanne Jelin, whom you probably know, like from Harvard, Anna Sørensen from the Niels Bohr Institute in Copenhagen, and two experimentalists, Amit Bahadi and Thomas Volz. And so again, this being the ITAMP Fest, let me just point out that the theorists here at some point in their careers all have been at ITAMP as ITAMP fellows, actually. Okay, so let's go into the physics here. So laying just the foundations of what I will tell you is like kind of if you excite semiconductors with light, then under conditions where the incident light does not carry enough energy to promote electrons from the valence to the conduction band, there are, under certain circumstances, still resonances that lie energetically within this band gap, corresponding to bound electron-hole pairs that we call excitons. So I won't go into any more detail, just to give you the idea that excitons are basically like atoms that you produce optically in a semiconductor. The other key ingredient for my talk are Rydberg states. So here, just shown for atomic states, actually. The idea being that as you increase the principal quantum number, for example, hydrogen, these states get huge very fast, and their interactions grow massively with this principal quantum. Okay, and then like kind of the use of these Rydberg interactions is then to implement blockade. So here you see that two ground states can be excited. I mean, if you have two particles, excitons or atoms, you can excite one of them to the Rydberg state, but not both. And this is because like when you excite both of them, sorry, Mariella, when you excite both of them, there's an energy shift that you would have to pay, and that's usually excessively large because of these interactions. Okay, so now we'll use like these ingredients, basically excitations and Rydberg states, for some interesting physics. And so the first strategy is to build a nonlinear quantum mirror. So the material in which these excitons live can be semiconductors, and I will be talking about two classes. And the first one is this two-dimensional class. It's called TMDs. Let's not worry about the real name. And they're really interesting. They for all sorts of purposes, but here I will just use that these materials are perfect mirrors. And that has been seen in Misha Lukin's group and here at Harvard, that if you illuminate one of these flakes, then actually on resonance with the resonant with the excitonic state, then it lights up in reflection. You get almost perfect reflection. And then just to test, if you remove this resonance, then this reflection is gone. So these states, like these semiconductors, also show Rydberg states. This is just like to remove any concerns if you have any. Okay, so let's say like we have these excitons. They can be excited to Rydberg states. So first, let's ignore the Rydberg state and let's ask what happens if I shine like single photons on this mirror. So because it's a mirror, then actually you will see that like a single photon will just be reflected off this. But now there's a trick called electromagnetically induced transparency, or EIT, by which you couple this low-lying exciton state to some long-lived state. So in this case, it's the Rydberg state. And now EIT enables the formation of a dark state and kills all absorption. And so like if you send single photons through this mirror, then actually they will pass through as if there was no mirror. Or as if there almost was no mirror, because I mean they're not absorbed, but actually they get, it takes a certain time for them to pass through the mirror. So a photon comes, that gets a slight time delay while it passes through this mirror, then it travels.
Changes its frequency or wavelength?
No, we will come to that, but that's
the time delay. I would expect like with water, for example, you can think that they go slower somehow.
right. I mean, like kind of in a bulk material, it would change its root velocity and then like pick it up again. Here, there is no. I mean, the material is like has no thickness, so it's like a delta barrier through which you go, but it still takes some time to get through. Right. So so now what happens if you send multiple photons onto that mirror, then like they all get there, and like kind of one of them can get through. And while it gets through, it produces a dark state, this EIT dark state. But when there is the EIT dark state, no other photons can utilize this EIT pathway, and then they see like kind of just the basic reflectivity of the mirror and are reflected back. So that's the simple picture. And actually, like this can be calculated exactly, and we see this confirmed. So here we look at G2, the photonic correlation function behind the mirror, basically. which is uncorrelated at large photonic separation. So asking like kind of when do I detect a photon at time 0 and a certain time later. But there's a very much reduced probability of finding two photons in close separation. And actually intuitively, like kind of the time it takes for this correlation to reach its original value at 1 exactly corresponds to the time it takes the single photon to travel through the current. So then if you drive more strongly, there are actually like some interesting effects like Rabi oscillation is happening here that can also be computed exactly. So the point is that these kind of like this anti-correlation here, or like kind of this very much reduced probability of finding two photons in transmission at the same time, is a signature of quantum light. So here we can already see that this light that is produced in transmission is a form of quantum light. And this value is actually very low, and it's also stable against decays that you could have in the system. So just to show you that this is very low, like kind of current experimental records for other excitonic systems like produce a G2 that's just below 1. Here, those are these papers. It's a slightly different system, but I think like it's kind of promising to use with this, to work with this reflectivity to really produce that kind of this quantum light in the sense that I described to you.
So what is the anti-function essentially, right?
Right.
This is the only form of quantum light?
No. Plenty of forms of quantum.
How to masquerade?
Yeah. Okay, so the second strategy, how can we also produce a quantum light? And this is something that I'm very much working on right now. So the results you'll see now, I produced yesterday and this morning. So most of like some of them at least. And so like we're just this is a little later than yesterday, yeah. And that's a photo I didn't take myself. So it's this other material called cuprous oxide. Don't worry about it. The only difference that I want you to have in mind is that it's not two-dimensional. This is actually a bulk material. It's a crystal. And that's like kind of the absorption pattern that we see. And basically like this, like if it looks red, right? And so there are two important optical properties this material has. One, it has a fairly weak optical coupling. So the absorption length, so kind of like when does the intensity of light drop to a certain value is like on the order of tens of microns. So that's low. And it has a significant absorption background, this one that is not related to excitons. So both of these feature or like these properties are not very conducive to inducing photon correlations. But maybe there's a way of doing it anyways. And so let's calculate this. So this is my model of a semiconductor, and we shine in. Oh, that's great with this. Sorry. We shine in a Gaussian beam here, and like this Gaussian beam now produces excitons. So an exciton could sit here, and then it produces a certain radius around in which no other exciton can be created. So now there's actually a very, very good chance. I mean, like for one, like photons traveling through this medium mostly don't produce an exciton because the optical density is so low. And then, like when you create an exciton, then it can decay and emit a photon again into the same mode, but it might as well produce a phonon and be gone. And actually, the probability of producing a phonon and be lost outnumbers the probability of emitting into the same mode about 50 to 1. So it's actually kind of questionable, like could we even like ever get like some sort of photon correlations? But it turns out that I solved this the correlated propagation of two photons through this medium, and actually you see directly that for G2, like the photon correlation at the output, this background doesn't matter. And all of these loss properties aren't so important. So like this entire problem can be characterized like by the light matter by the light exciton coupling parameter beta that basically says like what's the probability of the photon to get back into, or like of the excitation to decay back into the photon or to decay into something else. So that's this factor that's 50. And then there's the tuning. So what's the frequency of the incident light compared to the exciton? And so it turns out that there's an effective potential between the photons, which is different at different detuning. So here would be on resonance. On resonance, you have like the solid lines are absorption, so you get like massive absorption at short photon-photon separations, and you get some refraction here at intermediate ranges for the photon-photon separation. And at negative detunings, you get basically this very regular-looking photon interaction, and at positive detunings, so you can get a resonance structure. So now let's look at what happens to the photon-photon wave function. So we start here, maybe you can't really see it here, there's a line at 1 in each of these plots. As we propagate through the medium, there's like some shape coming up in all of these cases. And we see that at the output of the system, we actually do get like some interesting dynamics here that looks very different, like on resonance, on the red detune side, and on the blue detune side. Okay, so now let's just to give you an idea, like how do we now understand this two photon process? So this is kind of the two photon wave function after propagating for 5 absorption events on resonance through a crystal. So you see an imaginary and the real part. And so we can Fourier transform this, and it actually gives something like this. And here, like this gives us an information on how, like the two photon energies, how they're correlated in energy. So you see, kind of there's a hump, or like kind of an increase at some positive energies and some negative energies. So this must be symmetric. And it basically says that an incoming photon pair that's uncorrelated in the beginning can undergo some scattering by which it becomes entangled. So here we get one photon that's redshifted with respect to the incident frequency, and one that's blue shifted. And these are kind of these two humps that we see here. So in other words, in the words of optics, this would be a 4-wave mixing process. You have 2 waves coming in, and you have 2 waves going out that are red and blue frequency shifted. Okay, so yes, absolutely. This is so the wave function, it's the continuous wave calculation. So like kind of it's in relative, like the relative coordinate is always 1 if there's no correlations. And here, this is the deviations from 1, so delta E.
But the fact that it will take longer and longer time, so you get essentially the state sort of down state. So that would say that you have a long state.
Yeah, this is kind of
so if you have long state, there should be some interaction.
Right, there is an interaction. This interaction is just like the interaction is this interaction potential effectively between the photons. And some people would call this a photon bound state, like kind of a 2 photon bound state. I don't like this term because as soon as the 2 photons leave the crystal, they still have the same separation, right? Like when they are frozen in time, like they leave the crystal and then they just fly like this, no change. But is that really a molecule or like kind of a bound state? They're just like yeah, but I mean, there's no binding force. I think it's semantics, but like some people would call that a bound state. But without a binding force, I will not call it a bound state. Yeah.
So these probably just come in pairs. That's what you are saying. It's not that they are really bound. Just are somehow.
So initially they're like, think about the long pulse, where the position of the photons initially is arbitrary. So it's a flat distribution for the first one, flat distribution for the second one. Now you go through the crystal, and afterwards, there's a massive probability that they have a certain time separation. So if I find the first one here, then very likely I find the second one, like whatever, 1 second later. And this translates in frequency to, if I Fourier transform this also would send it through a spectral analyzer, then I would see one that's redshifted and one that's blue shifted, and they're entangled. So this is what I like. This is energy time entanglement, right? Like if I detect a blue photon, I know that there's a red photon on the other side.
And some people call this entanglement for bound.
And you can call them bound states because they have a fixed separation. So, and the last strategy is actually like one that really is not so much theoretical, but there's like, I just did like some theory support work here for like really coupling excitons to cavities. So it's like kind of similar to what Valentin said, except in the limit where this where the light matter coupling actually is in the very, very weak coupling limit. We call it the strong coupling limit here, but it's actually in Valentin's language, it's the weak coupling.
Yes, of course. When you find a positive redshift, then you find the second one. This is because of
Yes.
Okay.
There must be conservation of energy.
This is the reason why taking this coupling this way.
I don't know what you mean reason. I mean, it's like it has to be that way, right? Like you cannot lose the energy of the photon somehow. So they have to be correlated. If you shift one red, you better also shift one blue.
Now one photon is given energy to the other one.
Right. So this is like kind of like with this, like we started with this like kind of two photons propagating, like coupled to excitons, the exciton interact. But like this process in the end can effectively be interpreted as one where the photons go in. I don't really care like what happens to the medium, but it's like kind of a four-wave mixing process where these four waves, like kind of the two incoming, the two outgoing waves, mix in such a way that like one is blue shift, one is red shift.
It's like a scattering problem.
It's like it's like a scattering problem. Yeah. And so like kind of I can skip probably this slide here. Like kind of one way of like traditional way of producing quantum light is to couple strongly to some excitation in the cavity, and then use interactions. So and that was actually kind of difficult, like especially for a material like copper oxide, because as I said, right, like the light matter interaction strength is weak. So getting into a regime where you get these quasi-particles, the polaritons, mixed states of light and matter that Valentin was talking about, is difficult. But the group of Hamid Wahadi managed this, and like this is what you see here. So these are kind of like the exciton lines that you see in black, and multiple cavity lines that you see as these parabolas. And whenever the parabolas cut the exciton lines, you see that there's a splitting. And that splitting is probably better resolved here, and you really see like a lower branch and an upper branch. So really like mixed mixed particles that are half light and half matter. And we see that for n equals 3, 4, 5, and like now they're pushing towards higher. That's the light matter, or like that's the light matter coupling. And here they kind of we show you like kind of the strong coupling limit and where the experiment is. And as soon when the experiment is over, it's like then like here, and here, you're in this what we call, or like what in this polariton community outside the ultra strong coupling is called the strong coupling limit. Yeah. Okay, so that brings me to the end of my talk. Let me just like give you some conclusions. So in the first strategy, I showed you that like two-dimensional mirrors can dynamically change their reflectivity in response to single photons. Then another strategy was to kind of transmit pairs of uncorrelated pairs of photons through some very lossy material and see like how they get entangled after they pass through that medium. And the third strategy is to use Rydberg cavities, where you get strong light-matter interactions. But here, actually, the Rydberg interaction, so the nonlinearity, hasn't been proven yet. So that's like an outstanding problem. But I think like this third line of research is like one where you overcome loss and where it becomes almost deterministic. You send in 2 photons, you do get a pair of correlated states. So that's very interesting also, like in terms of prospects for quantum many-body physics with photons. Right, and so basically the bottom line is that Rydberg blockade is an alternative mechanism to entangle photons with interesting prospects on top of like kind of parametric down conversion performance. Okay, thank you.
The lifetime of, because you then excite the reference state.
It's always okay. So kind of the lifetimes for the ground states is in the line width is in the milli-electron volt range, so it's like very short. So think like terahertz of picosecond. And then if you go to the like 3 orders of magnitude longer, if you go to the Rydberg state.
Okay.
So yeah. And now, I mean, like, okay, so and like kind of expanding on that a little, now there are also other Rydberg or other excitonic states that live considerably longer. For example, if you like some of the very high line Rydberg states, some of the very low line Rydberg states in some material when they're dark, and some excitons in special geometries where the electrons are whole are spatially separated. All of these topics are interesting. I just brushed all of that under the rug. We can discuss.
So, ask this question. You send the light, and it's like one model layer, like a CMD,
Right.
And it somehow like the delays that. So, but then you said there's no wavelength change, so there's no group velocity change.
Right, like you basically imprint the phase.
Basically,
You imprint the phase on the beam, right? Like you kind of, let's say you have a Gaussian beam that travels, and there's an optical element, and afterwards it has a phase.
and this happens because of the interaction of the photon and the model layer.
Right, so it becomes like for a certain amount of time, like the photon becomes one of these dark state electrons. So it becomes actually part excitation, and then this excitation gets converted back into the beam. There, the nice thing is that conversion is perfect. So you kind of go in and out, no loss.
It's kind of like a virtual process and how delay.
Exactly. I mean, virtual, I don't know, you can't detect excitation.
detect
You could, in principle, if you detect it and you don't.
Theoretically, that you were able to describe it.
No, you can't. I mean, if you were to monitor the Rydberg state, you would see it. Yeah, it's an interference. EIT is an interference mechanism by which you go in but can outcouple perfectly.
But don't you have to worry about electricity transgate when you go from just pure light into our transect? If you switch too fast, right, then you can go away.
That's true, but this is in the continuous wave. So you kind of like you just have a photon that's very long.
Okay, then fine.
Yeah.
I don't know very well, but the research paper about neurons, about from the loss group, they use this target on.
Right.
There are some connections.
There are very interesting connections. Yes. So you can basically like like the paper that Matteo is referring about to is one in the Box group where in the Emmanuel Box group where you have basically atoms on a two-dimensional lattice space at a spacing that's smaller than the wavelength, and that also becomes a mirror. And so you can also now exciting to the Rydberg states, which they didn't do, but want to do, realizes a similar principle by which you could switch the transmission. There are very interesting questions pertaining to the delocalization of the atoms for the excitons in this case.
Thank you, Valentin, and everyone else.
Thanks so much.
Yeah, yeah.
So now we can both log out and we'll finalize the recording.
Where is this recording right now?
You did log out?
I'm totally confused.
You have to go.
This one, right? No?
Yeah, just hover there. And then, kind of it has to get dark.
I don't know actually, but no. Like, where's the? Maybe somebody works.
So if I plug you right, you don't need to.
Right, yeah,
Yeah,
Yeah, I know.
I could just end the meeting.
You just, yes.